Okay, so the last 2 weeks we've been looking at Turing machines and considered these two kinds of Turing machines: the kind that recognize languages, so have the accept and potentially reject states, and the kind that compute functions. And because Turing machines compute with words on a tape, the written tape contains characters, they compute functions from words to words. I'm going to begin with something relatively straightforward, but it's just a very minor generalization of what we had 2 weeks ago. And then I'll use that as a lead-in to take us to the main topic of today. So the first part of the lecture should be relatively gentle, just for a short while. So we considered 2 weeks ago what it means for a Turing machine to compute a function from words over an alphabet sigma to words over the alphabet sigma. One can naturally generalize this to words over an alphabet sigma 1 to words over a different alphabet sigma 2. So let's just write that down. So a TM computes a function, and as always we're going to be looking at, in general, partial functions. The reason for including partiality is because Turing machines may compute forever and not give, and never give us an output. So on some input words, you won't get an output. Or with the way we're computing with Turing machines, we only get an output for when we're computing functions the way I've defined it if we get into the hold state. So a Turing machine might also terminate in different erroneous states, say, and that also, then on that input word, we also don't get an output. So we're computing functions from input words to output words, but they're not always defined. And the TM computes a partial function f from one alphabet sigma 1, from words over one alphabet sigma 1 to words over some other alphabet sigma 2, if, well, we just require what we had before, which is, but just generalize it appropriately, which is that all input words sigma 1 star, if the input word is the domain of f, it belongs to the domain of f, so if W belongs to the domain of f, then the Turing machine is M, then we execute M on W, and that terminates in the hold state with f of W on the output tape, sorry, on the tape. And if the word is not in the domain of f, then M on W, meaning if we execute the Turing machine, M on the input word W does not terminate in the hold state. And this is basically exactly as it was before. As before, we require, when we get f of W on the tape, what we mean is that's the only word on the tape, and moreover, the head position is at the leftmost character of this word, unless it's the empty word, in which case the head position is pointing for the empty square. But this is exactly what we had before. There's only there are slightly different assumptions on the Turing machine, because now the Turing machine needs to have both the alphabet sigma 1 and sigma 2 on its tape language. So the first one is that both the alphabet sigma 1 and sigma 2 are in the tape alphabet, and they don't contain the blank square. And secondly, again, we have distinguished halting state. Halt. Okay, so there's basically nothing different. The only thing is that we're allowing to change we make sure that, that we allow the Turing machine to change the alphabet of the words as it computes. And to do that, it just needs to contain both alphabets, which may intersect, they may not, in its language, and they may be the same alphabet. Okay, so that's a very mild generalization. Before moving on from this, I want to consider some simple generalities about computing functions between words over different alphabets. So the first one is the identity function which I'm going to write like this: 1 on sigma star, the identity function on the set of words over the alphabet sigma. So this is the function that takes a word and maps it to itself, sigma star to sigma star. This is computable. Of course it is. The Turing machine doesn't do anything, it just goes into the accept state. So here I was defining, on this board, I was defining what it means for a Turing machine to compute the partial function, and then we follow that up with the definition that a partial function is computable if and only if there exists a Turing machine that computes. So the same as before. The identity function is trivially computable. And secondly, the computable partial functions are closed under composition. So, in other words, specifically, if f from, let's say, f1 from sigma, words over the alphabet sigma 1 to words over the alphabet sigma 2 is computable. So I should be writing partial arrows. So the notation on this calls for a partial arrow is you miss the bottom bit of the arrow. So I should have really, strictly speaking, written that here as well. So a partial function from words over sigma 1 to sigma 2, and we've got another partial function from words over sigma 2 to words over sigma 3. And they're both computable. And so is the composite function. Composite obtained by composing the two functions. So that's the partial function f2 composed with f1, which goes first to f1, and then we do f2. That goes from words over sigma 1 to words over sigma 3. What I want to draw your attention to before we go on, so this is basic material here, only mildly, very mildly generalizing what we had in the first lecture. But one has to be a little bit careful about how one composes partial functions. So we're dealing with partial functions here. So of course, partial functions include as a special case total functions. So total functions are ones that are defined on the whole domain, and we all know what the composition of total functions is, and if we compose them as partial functions, we get the usual composition as total functions. But how do we compose two partial functions? So let's write that in a different color. So the composition F2 composed of F1 is defined away by, we take any W, which is going to be a word over, so the composition goes from words over sigma 1 to words over sigma 3. So we take any W, which is a word over sigma 1, and we map this to what we get by applying F2 to the result of applying F1 to W. So that doesn't look strange at all, that just looks like the usual formula. But the thing you have to be careful about is we've got partiality here. So what happens if F1 of W is undefined? Is it possible for F2 of this to be, for the whole composite to be defined? And we have to give the right, we have to decide on our definitions here. And the only sensible thing, the sensible thing to do is to say no. So the point you need to pay attention to is if F2 composed with F1, the composite function applied to subword W is defined. So the notation, I think I've already used it, but if not, I'm introducing it now, and it's introduced in the first page of the notes. This means this application of this partial function is defined on the word W. That's defined. Well, if that's defined, that implies that F1 applied to W is necessarily defined. So when we do a composite, if we apply the first function and we get an undefined value, the result of the composition is also undefined. So, okay, that makes sense. I hope it's not problematic. The reason you have to pay attention is for cases like the following. So, in particular, you have to take a little bit of care. If F2 is, say, some total function, some constant function, total function that always maps everything to the same result. So, for example, if F2 is y maps to 0, so everything is mapped to 0, then if F1 of x is undefined, so I use the up arrow to mean undefined, nonetheless, F2 of F1 of x and F2 of F1 of x is also undefined. So although F2 maps everything to 0, it only maps things to 0 if you actually give it a legitimate argument. If you've become undefined here, then you stay undefined. And if you think about how you prove, which you may have done in an exercise class, how you prove that computable partial functions are closed under composition, what you do is you start off with a Turing machine for F1, you run it, and if it gets to the hold state, you then stay with the current tape and head configuration that you've got, and you then run the Turing machine for F2 on current tape and head configuration. Doing that combination, first run a Turing machine for F1, then run a Turing machine for F2, you end up with a Turing machine for the composite function F2, F1. And that only works, that way of doing things only works if you make this convention that if F1 of W is undefined, well, we can read this backwards, if F1 of W is undefined, then the composite function is also undefined. Because if you run f1 is undefined, the Turing machine f1 might go into an infinite loop, and you'd never be able to start the Turing machine for f2. Okay? So the proof of this relies on having the right definition of composition of functions, and this is the right definition of composition of composition of partial functions. It's just a little, for those of you interested in programming, specifically functional programming, there's a little connection to make here. So this way of composing functions is what works automatically if you use what's called an eager or a call by value functional language, such as Camel or OCaml. That's I guess the program in OCaml. That does things this way. If you use what's called a lazy functional language, like Haskell, then actually a lazy functional language only looks at its argument if it needs it. The lazy functional language does not compute the correct composition according to our composition of partial functions. Okay, that's just a side remark for those of you who are interested in that sort of functional programming. Right, so having made those introductory remarks, so a mild generalization of what was in the first lecture, we now come to the main point for today, which is, well, there are two main points, which is that the current view of the world of what we can compute in terms of functions is a little bit limiting. So currently we are computing functions between words, and it's functions, moreover, of one argument. We give them one argument, that's a word, and it gives us back a word. So that's very limiting. Computability is not just about words. Computation is not just about words. And it's very useful, obviously, to often compute functions that have more than one argument. So far, we have computability for functions of one argument. Such functions are called in English unary functions. So unary means functions of one argument on words. So we naturally immediately want some desired generalizations. So, firstly, functions of several arguments. One's used to in mathematics, when one moves from single arguments to several arguments, things get more complicated. Like calculus in one variable is much easier than calculus in several variables. For example, calculus is like analysis with differentiation and integration and so on. So we want to move to functions of many arguments, potentially. And rather than being limited by words, I mean, the computer science way of saying it would be functions on other data types, not just the data type of words. And in order to make it less computer sciencey, let's say on other types of data instead. Right, well, same thing basically, other than words. So these 2 points are what we're going to address today. We're going to do it using a quite general and powerful framework for looking at functions on other types of data. But in fact, that's the main question we address, functions on other types of data. Is once we've got a sufficiently powerful framework for looking at functions on other types of data, we can then look at functions on many arguments as a special case of functions on other types of data by having product data types to give us, we can capture the several arguments. So functions acting on product data types, we give the several arguments in a tuple. So we're basically going to start by looking at functions on other types of data. And let's begin with basically the simplest possible example. Well, no, it's not the simplest possible example, but a very natural and nonetheless simple example where and it's an example which is often the starting point for courses on computability theory, and that's functions computing with natural numbers. Very hot in here today, isn't it? And let's talk about computability for functions natural numbers. Now, having got the Turing machine model, we don't want to change our model of computation. So what we want to do is work with the model of computation we've got. We want to say how using the Turing machine model we can compute functions on natural numbers. And it's kind of almost obvious how to do this. So the Turing machines can compute functions on natural numbers by representing natural numbers as words. And of course, there's not a unique way of doing this, but there are some natural choices for how to do this. So for example, we can represent natural numbers, and probably you did this in the exercise classes, you computed some functions on natural numbers potentially in the exercise classes. I guess I don't know if you did, but the very natural thing to do is to represent natural numbers similar to how they would be represented on an actual computer as binary words. So e.g., use the binary alphabet. The alphabet consisting of the 2 bits. And will represent a natural number n using its binary representation that's a word of bits. And at the moment, this is a little bit ambiguous. Can anyone see what's potentially ambiguous here? Well, so yeah, potentially, you can say, well, the binary representation is the standard one as we would write it, in which case it's not so ambiguous because you would never write 3 in binary as you wouldn't really write it as 0, 1, 1, you would write it as 1, 1. But we should specify a little bit better. So let's say it's binary representation without leading zeros. So for 3, 1, 1 is okay, so let's give that a tick. 0, 1, 1 is not allowed, 0, 0, 1, 1 is not allowed. What about 0? Well, 0, if you represent it as 0, it kind of has a leading 0. The sort of nice mathematical answer here, if we're not using leading zeros, is to represent 0 as the empty string. So the little curly epsilon is the empty string. Okay? So we'll do that, and then so we won't represent 0 as 0, but every other number would be represented the way binary number would be represented the way it should. Okay. And now it's easy to define very happy with any of the pens here. But anyway, now it's easy to define what it means for a function from natural numbers to natural numbers to be computable. So squeeze it to the bottom of the board here. Partial function f from natural numbers to natural numbers is computable. Definition. Well, what do we want it to be computable? Well, we want a Turing machine that, given a representation of a number in the input as a word, will give us the word that's a representation for a number in the output. So we've already said what it means for a Turing machine to compute a function on words. I mean, we've already defined the notion of computability for a function on words. So we can forget the Turing machines and just think about the functions on words being computable. I mean, Turing machines are there computing those functions in the background, but we don't really need to explicitly refer to them. So it's computable if there exists a computable function on words that computes this function on its representations. So if exists a computable function G, partial function G, from binary words, so the words over the binary alphabet B itself, such that so what we want to say is for all numbers, if f of n is defined, then G is defined on the binary representation of n. So f of n is defined if and only if. Sorry, we want. I mean, I'm going to write the same thing, but I think it's more. It explains it better to write it the other way around because we're looking at constraints on G. So G is defined on the binary representation of n if and only if f of n is defined. And in the case that f of n is defined, sorry, this is G is defined on the binary representation of n if and only if f of n is defined. In the case that G is defined, and equivalently f of n is defined, then obviously G should compute, G applied to the binary representation of n should compute the binary representation of f of n. So G G find. But usually that's like this. If that's value is defined, then we apply G to binary representation then, and that gives us the binary representation of that. Okay. So, very natural definition. I'm going to play on this theme a little bit about how we might have defined this in alternative ways in order to, so this is natural, but it's not the only way you could do it. And although this is a very, very simple example, I'm going to consider 3 other possibilities one could do as a way of illustrating some quite abstract machinery that will be then very useful. And that abstract machinery is about how we can talk about computable functions on basically arbitrary types of data. Okay, so that's quite abstract, but hopefully as a nice way into it, we're going to be looking at different ways that one might compute functions on natural numbers as a sort of simple illustration of the idea of what we're going to use to represent arbitrary types of data. So, I mean, this is the way I'm going to do it, and I've written the notes like this. The benefits of doing it this way are we introduce the abstract concept using quite simple examples. The drawback of doing it this way is we're going to have to spend quite a bit of time thinking about how to represent natural numbers, which is a problem we've already solved and is actually quite a simple, is quite a simple problem. So we're going to, you know, just think about how we could do a simple thing in some other ways and hopefully get some benefit from that. Right, so, oh, the camera was again out of focus there, but never mind. A bit late now. So let me start with a second approach here, which is if you're programming functions on the natural numbers in this way, I mean, depending on what program you're writing, but it might quite often be the case that you write a program and at the end, your natural algorithm will give you some output that has leading zeros on it. So for example, your algorithm for subtraction might naturally leave those leading zeros in place. And of course, you can then, once you've had such an algorithm that leaves a number with leading zeros, you could then have a little bit of routine at the end that goes along the tape and cleans up the leading zeros, so takes away the leading zeros. So there's no problem sort of in getting algorithms into this form, but it won't always be the natural form. So another natural representation is to allow us to compute with arbitrary words over the binary alphabet. So any word over the binary alphabet represents a natural number using its binary interpretation. So why not just compute with arbitrary words rather than just these special ones? And then how would we represent that? We can't quite use a definition like this, because we no longer have a function that takes us from a number to its binary representation. The function goes in the other direction. It goes from the words to the number. So the arbitrary words are representing numbers, and several different words will represent the same number. So to say how we compute with that, we're going to look at something called the representation, which is a mapping from words to the set that's represented. So a different representation and the representation has the following data. So the representation says the representation has an alphabet associated with it. So again, our alphabet in this case is the binary alphabet. The representation has a function associated with it, and this is the function that tells us, given a word representing a natural number over the representing alphabet, which natural number do we represent? Now, in general, such a function might be a partial function. We don't need to have every word represent a natural number. In the case that I'm talking about now, binary representation allowing leading zeros, this is going to be a total function. So we're going to have a total function, and I'm going to call this function here gamma sub n for representation of the natural numbers prime. So because it's going to, actually we're going to have another one that will use as the primary one. So we know what sigma b is. We want to specify a total function. So the representation gamma prime of n applied to a word, a binary word, is going to be defined as, well, we want it to represent the binary number obtained by the binary interpretation, so we can get that by summing from I equals 1. Let me take the formula from my notes. I mean, there's so many ways of writing it, but I might as well write the same formula in the notes. So from I equals 0 to the length of the word minus 1. So if you read the first page of the PDF notes, you'll see that an arbitrary word of length k, I represent the individual characters of it as W0 for the first character up to W of k minus 1 for the kth character. It's like using the sort of computer science conventions that one has for arrays in programming languages and indexing in strings in most programming languages, and one starts counting at 0 for the first character, which gives all programmers headaches until you get used to it. Anyway, so we're going to count from 0. But we want the word, we want the least significant bit to be the bit on the right, the character on the right, so that's the bit with index. If this has length k, that's the bit with index k minus 1. So we'll have I for the significance, so powers of I, so powers of 0, powers of 1, powers of 2, so times 2 to the I, so when I is 0, we're going to have for that we want length of the word minus 1, so to get that we want the character in position length of W minus I minus 1 times 2 to the I, and that gives the binary representation. Okay. Well, that's one representation. So this is binary with leading zeros. Another representation is to use, instead of a binary representation, what you might call a unary representation, which is just to use an alphabet with one character. I'm going to call this gamma prime prime, the natural numbers. So another representation of natural numbers. So here we're taking words over the unary alphabet, which I'm going to call sigma u. Again, it's a total function to the natural numbers. So here, the unary alphabet is defined to be, well, an alphabet with just one character in it. Let's call it 0. It doesn't matter what we call it. You might find it more natural to call it 1, but anyway, I'm calling it 0. And this is unary representation. So words over this alphabet is just a sequence of zeros of some length. Those are the only words we have. So we've got the empty strings, the sequence of zeros of 0 length, 0, 0, 0, 0, 0, 0, so on. So this representation is really easy to define. The gamma, so the natural number interpreting a word W here is simply, what's the easy way of defining this? Length, very good. So just the length of the word W. So one could compute with this representation of natural numbers. What are the disadvantages of that? I suppose it takes a lot of space and hence a lot of time to compute with it, because these words are exponentially longer than the words represented using the binary notation. Nonetheless, for the point of view of is it computable if we allow unlimited space and time, which is what our notion, we're looking here at computability rather than complexity, we're not placing resource restrictions. Actually, this representation turns out to be equivalent to this representation. In practice, you wouldn't use it. Although, for those of you who know about a subject called type theory, and there's some interest in type theory here, type theorists essentially do use this representation. It's part of the inefficiency in type theory if used in a naive way, if used computationally. Anyway, I'm a bit afraid of this statement being on a video, but anyway, it's too late. I've made it now, and I'm not going to edit the video. Anyway, so those are two representations. Plus, we've got the original representation here. But notice that the first representation we use looks like it's of a different form, because here we have the function going in the opposite direction from natural numbers to strings. However, we can recast exactly this representation, the binary representation without leading zeros, in the same form that we've got here. So let's use our first representation again, the original first representation in a different guise, so in a different form, where we put the function the other way around. So this is why I was using the primes here. I'm going to keep our original representation as the kind of canonical one, so to speak. So this is our chosen representation for the natural numbers. This is again a binary representation. We now want to map binary words to the numbers they represent. But in this case, not every binary word represents a number, because we're not allowing the leading zeros. So this is an example of such a representation where we have a partial function rather than a partial function rather than a total function. So this is again binary without leading zeros. And this is defined by, well, to define this, we need to say what this partial function is. So to do that, we'll give the domain of this partial function, the set of strings on which it's defined. So the domain of this partial function is simply all those binary words that do not have a zero as the first character. We can define that as the the empty word together with all words beginning with a W. So we can write any word beginning with a W as one concatenated with some other arbitrary word. So here, W is some arbitrary word. Some other arbitrary binary word. So that's the domain of gamma n, and then the definition of representation on the word W is, well, it's the same formula again that we had here. We're interpreting on a word that has no binary, no leading zeros, again interpret it as interpret the binary word as giving a number in binary representation. So it's the same formula. I is 0 to length of W minus 1. Well, let me write it out again. W of length of W minus I minus 1 times 2 to the I. So here we have three different representations of the natural numbers, all now essentially in the same format, but they are all partial, total functions are trivially partial functions. Moreover, they're not just partial functions, but they're surjective partial functions, in that we're representing natural numbers. To represent natural numbers, you want every natural number to be represented. So I'm going to use another notation for surjective functions. We're going to make double-headed arrows. So let's make these. So here we've got surjective total functions. And notice the first two are total, and the second and third here are also injective. So they're bijection. There's partial total bijection, bijective representation. This is a partial bijective representation. But nonetheless, we've got three representations. They all have this form, mapping of a partial mapping from representing strings onto that surjective onto the set that we're representing the natural numbers. Okay, so that's a good stopping point. I've overrun by 5 minutes, and we'll have the 15-minute break. We'll start again at 20 past. Right, so we've defined here three different representations of the natural numbers, ways of encoding natural numbers as words over appropriate alphabets. They're not the only three representations. You can think about some other ones if you like, but we have three different representations then. Natural numbers, namely gamma sub n, gamma prime sub n, and gamma double prime sub n. So what I want to show you now is how, using this style of representation, we can give a uniform definition of what it means to compute function of what it means for a total function or a partial function on the represented set to be computable. And then we could instantiate that definition using any of our representations of the natural numbers, and we have three potential definitions of what it means for a function of natural numbers to be computable. Fortunately, all of them coincide, and all of them coincide with the definition I've already given of what it means for a function on natural numbers to be computable. But the point is not just to recover in several different ways the same notion of computability that we've already given for functions on the natural numbers. The more major point is that the notion of representation underlying this is very general and very powerful, and we'll see it applies to many other kinds of data type too. We're not going to see so many today, but throughout the course we'll see many other kinds of data type treated in this way. And using it, we can give essentially a uniform definition that applies to any such any set that has this kind of representation. we have the appropriate notions of computability for such sets. So I now want to abstract from what I've done here for the natural numbers and give the general the general definition of a representation. The definition, a representation of a set X is given by an alphabet of, actually let's say using an alphabet sigma is, the definition is it's simply a partial, or I'm going to write it the other way, a surjective partial function, or a partial surjection, a surjective partial function gamma from words over the alphabet onto a partial function onto X. The point is, it's partial because we don't require that all words over the alphabet represent elements of X, some set of words over the alphabet are representing elements of X, and it's surjective because every element of X has to be represented by at least one word. It can be potentially represented by many words, but it has to be represented by at least one word. Just a simple remark. So alphabets are assumed to be finite. We always want our Turing machines to be specified by finite amount of information. So if sigma is finite, non-empty, the set of words over it is countably infinite. We've got a surjective function from a countably infinite set onto X. So that means that X is itself a countably infinite set. So a set can only have a representation if it is countable. As the natural numbers is, so we didn't have problems giving the natural numbers a representation. So now I want to come to the main reason for introducing the notion of representation, which is to define what it means for a function between represented sets to be computable. More generally, a partial function. So I think I need the whole board for this. So let's go to the other board. So in the notes, in the LaTeX notes, I've gone straight in at the deep end, so to speak, and just directly given the definition of computable partial function between represented sets. And actually, partiality here causes some slight complications in the definition. And I think from the lecture perspective, from the lecture, it's a good idea to see the definition of what it means to represent a total function, what it means for a function between represented sets, a total function between represented sets to be computable. I think it's worth seeing that definition for total functions first, and then how it generalizes to partial functions. So this is not explicitly, this next bit for total functions is not in the LaTeX notes. So given, the idea is we want to consider functions abstractly between sets and what it means for them to be computable. In order to make sense of that, well, computable means essentially computed by a Turing machine. We can't compute with abstract sets, we can compute with words, a Turing machine computes with words. So we can make sense of this if the two sets, the domain and codomain set, both have representations. Then we can talk about what it means to compute a function between the sets. So we're going to assume two sets. Let me be consistent with my notes, so we'll make them x1 and x2. So given representations, two sets x1 and x2. So the gamma 1 in general is going to be a partial surjection from words over some representing alphabet for x1, sigma. So sigma 1 is the representing alphabet for x1, and similarly we're going to have a gamma 2, which is a representation of x2 using a potentially different representing alphabet sigma 2. So given two representations, a total function f from x1 to x2 is computable if there exists a computable function on words that represents that function f on sets. So to say that, we say if there exists a computable, obviously we want a computable function on words, we know what it means. That was at the beginning of the lecture. We know what it means for a function on words between two different alphabets to be computable. I'm going to go here. But even though we're representing a total function, we allow the function on words to be a partial function. And this is important. The definition would be wrong if we didn't allow this in general. A computable partial function G, mapping words over the first alphabet to words over the second alphabet, such that, so S dot T, so two things hold. For all x, for all elements x in x and w and names w of x. What does that mean? Well, that's something I forgot to say on this board here. I think for people watching the video, I'm not going to move the camera. You can just hear what I write on the board because I'm going to say it out loud. So under the definition of a representation, we say that so gamma is a surjective function from words over the alphabet sigma to x. We say that any word w over the alphabet sigma such that gamma is defined on that word and its value is little x for some element little x in the set is a name or realizer, that's another word for it, of x. So we're thinking about representations as naming elements of the set x, the set capital X, by strings, so by words. So the words that represent a little x are called names of x. And we require that for any x in the set and for any name w of that x, we require that g of w is defined and G of W is a name for f of W. Sorry, not for f of W, for f of x. In other words, gamma 2 of G of W equals X. And that's all we need to define. So we can view this as a diagram. In that we have our two representations. Gamma 1, mapping words from the alphabet sigma 1 to x1. Gamma 2, mapping words from the alphabet sigma 2 to x2. We have our function f that maps x1 to x2, and we require that there exists a partial function g such that this diagram commutes in the sense that whichever way round you go, you get the same answer as long as you give it an input word that's in the domain of gamma 1. So the diagram commutes for all input words W belonging to the domain of gamma 1. So all those input words W that represent elements of the set X1. Or equivalently, for all W in the domain of gamma 1, it should be gamma 2 here. Gamma 2, gamma of G W is defined and equals F of gamma 1 of W. So it's necessarily defined because W is in the domain of gamma 1 and F is a total function. So this side is defined, so for it to be equal, this side must be defined. Okay, so that's what it means to compute, for a total function F to be computable. So can anyone see why potentially G might be, it's important, it can be important that G is allowed to be a partial function? It's quite a subtle question. Gives me a chance to take a sip of. So let me tell you that the point is that these requirements here say nothing about what G does for words that are not in the domain of gamma 1, for words that are not names, for words over the sigma 1 alphabet that are not names for elements in the set X1. Okay. And it doesn't matter if the function on words, computing F, doesn't matter what that does on words that are not names for elements of X1. So it could potentially, it's okay to potentially allow them to be allow G to be undefined on words that do not belong to the domain of X1. And it's important because there are some examples of representations in which if you don't allow G to be undefined on words outside, it's important, some things that should be computable aren't computable. And those are quite advanced examples, but nonetheless, there are considerations that it really has to be allowed to be a partial function here. But that's not something I can back up. It's not something I can justify right now, but just to be aware of it. Anyway, so that's what it means to compute for a total function to be computable. We'll now go to the more general case of a partial function being computable, and I think I need a different board for that. Right. You don't actually need this separate definition for a total function, yes?
what exactly this triple line and a line that?
Oh, sorry, right, I said this when I wrote it. This is an abbreviation for the English word equivalently. So this is the equivalence symbol, and so this says equivalently. I didn't. Yeah. So this is. So maybe I should. So this statement circled in red is equivalent to this statement also circled in red, which is equivalent to this. There's three different ways of saying the same thing. Okay. Actually, I didn't even need to make that definition at all, because now I'm going to define computability for a partial function, which is the more general case. And this definition is equivalent to what I've given on the previous board for when you consider the special case of total functions. So continuing with the representations gamma 1 and gamma 2, we're now going to say when a partial function f from x1 to x2 is computable. Again, if there exists a computable partial function g that does the right thing on representing words, that's on names. So again, if there exists a computable partial function on words of the relevant alphabet, so from words over sigma, relevant alphabets, so words over sigma 1 to words over sigma 2, such that so what do we want to say now? So the idea is the same, that we want on names of x1, we want g to do exactly what it should be expected to do. So if you've got a name for an element of x1 on which f is undefined, you're going to want g to also be undefined on any name for that element. And if you've got a name for an element of x on which f is defined, then we want to have the same condition that we have for a total function. So we can say that by making a quantification here. So for any little x in x and name w of x, name of x, name for x. That's 4, so let it be. So for any element of x, the represented set, so that should be x1, name w for x. So we require that if f of x is defined, then g of w is defined, and g of w is a name for f of x. So g of w is a name. So this is the same as what we have here. But we've got the condition now that f of x is defined. once. Secondly, is if GW is undefined, sorry, what's it like? If G of W is defined, then f of x is defined. Or you can read it the other way, equivalently, I won't write the symbol again, but anyway, equivalently, if f of x is undefined, then G of W is undefined. Okay, so it's not really very much more complicated. But we've got one more condition to take into account. And let me go back to the other board. So we can consider the same diagram here. Only f is now a partial function. But once again, the condition I've written for computing what it means for a partial function to be computable, once again, it implies, so if we change this f to a partial function, it implies that this diagram commutes. Or all words that are names of elements of the set x1. And it implies that the diagram commutes, but this diagram commuting is no longer equivalent to that. So the diagram commutes in this case, but the diagram commuting is not quite sufficient to get these two properties. So you can think about that offline, just a little warning that this is the corrective definition. I'm going to reformulate it because when, sorry, let's go back to here. I'm going to reformulate this in a more symbolic way, because when reasoning with it, it's quite useful to have the, one wants to do a sort of chain of reasoning. It's useful to be able to prove things by like a chain of equalities. It's actually useful to have a slightly different formulation, which is equivalent. So I'm just going to write that down here so that you've got it. It's also in the notes. Still hasn't moved. There we go. So equivalently, let's use the symbol again. I'm going to number these because it's useful to refer to them in reasoning. And now I do need to use my notes because I can't get this exactly right off the top of my head. So equivalently, for all words W that are names of elements of x1, so in other words, for all words in the domain of the representation function, we require 2 points. The first one is that if we apply representation function of gamma 2 to what we get from applying the partial function g to w, then that's sort of equal. So let me write the symbol straight away. Some equality symbol to f of gamma 1 of w. So this means equals, except there's a slightly fiddly point because we're dealing with partial functions. So here, all the functions are potentially partial. Gamma 2, gamma p, f, and gamma 1. They're all potentially partial. So any application can potentially give rise to undefined. And this relation is something that one writes It's a mathematical relation between expressions that are potentially undefined, and it's called Kleene equality, after Stephen Kleene. His real name was actually Stephen Kleene, but everybody now calls him Kleene because it's written like this. This is called Kleene equality. And it's defined by E1 is clean, so some expression that may be undefined is equal to some other expression that may be undefined, if and only if. Firstly, E1 is defined if and only if E2 is defined, and if E1 is defined, then E1 equals E2. So basically, this means if either side is undefined, then so is the other. And if one side is defined, then both sides are defined and they are equal. It's a bit fiddly, but it's kind of useful to use this relation whenever you've got expressions, when you're talking about equality between expressions that might be undefined, in order to essentially alert the reader to take care that we're talking about things, expressions that may be undefined. You've got some partiality there. Okay. So part of, I don't know how familiar you are in other courses with dealing with partial functions on a day-to-day basis. In computability, partiality is something you can't avoid because of the importance of programs that don't terminate in the subject, and the whole idea of the halting problem is it's impossible to decide if a program terminates, so non-termination is kind of fundamental to the whole topic. Partiality is very important in computability theory. We're going to use a lot of reasoning about partial functions. You're going to have to get used to this sort of notation and when to use it. And the second point here is a shorter one, so I need to find my black pen. Is that if G of W is defined, then G of W, so G is only defined on, so that we're only quantifying over names for elements of X1, G is only defined on such a thing, and if it's defined, it gives back a name for an element of X2. So G of W is always in the domain of gamma 2. Phew, goodness me. So the notion of representation is a very natural and not difficult generalization of the representations we saw of the natural numbers. But I hope you agree with me. I mean, there's nothing really difficult in the notion of computability for a total function and for a partial function. But as you can see, it's a little bit fiddly, so it's a bit subtle. So I mean, you know, you'll need to get used to it. But anyway, that we will do through familiarity. Okay, so we have the notion of computable partial function. I've already moved the camera. There are two other things I wanted to say here. So again, sorry, I'm not going to move the camera back, but So again, computable, so a function is computable f if we have a function g on words that essentially computes it. So I'm going to use the same terminology as earlier. I'm going to say that g realizes the function f. So we say that g realizes the function f. In this case, and now I've forgotten what the other thing I was going to say is. So let's carry on. I want to make two observations now about. We're in the setting that we're thinking about sets together with representations, and if we've got sets together with representations, we know what it means for a partial function between those sets to be computable. So I just want to remark that like at the start of the lecture, the identity function, the identity on x, so that x maps to x, is always, yes, now I remember what, is always computable. And the thing I forgot earlier, the other thing I wanted to write on the board is that, so what I mean by it's computable is it's computable from any representation to itself. So if a representation of x is called gamma, I'm going to say gamma to gamma computable. And on the other board, when I said that a function f from x1 to x2, the partial function is computable, this was assuming representations gamma1 of x1 and gamma2 of x2. So really, the correct notion here is not computable, but you should really refer to, if you want to be very precise, you should be referred to the representations that it's computable for. So if we wanted to be very precise, rather than saying computable, we would say gamma1 to gamma2 computable. It's computable with respect to the given representations gamma1 and gamma2. But actually, in practice, we're always going to be in the situation that when we've got a set, we have in the context, we already know what representation we're using for the set. So we're going to know what our gamma1 and our gamma2 is, and then we'll just typically say computable. But actually, while I'm giving basic definitions, I should put all the details in just to be very precise. So in this case, the identity function is always computable from a represented set to itself, where you use the same representation for the domain and the codomain, of course, use the same representation. And it might not be a surprise given what we started the lecture with, but the next statement is going to be similar to the start of the lecture, but also if we've got a partial function from x to y and another partial function from y to z, and x, y, and z all have representations, then the composite partial function, and if the first two are computable, then the composite partial function is computable. Actually, let's use x1 and x2 and x3. So if f from x1, that's a partial function from x2, is gamma1 to gamma2, computable. So gamma1 is our representation of the set x1, and gamma2 is our representation of the set x2, and g from x2 to x3 is gamma2 to gamma3 computable. Then the composite g composed with f, that's a partial function. We saw at the start how to compose partial functions. As a partial function from x1 to x3 is, unsurprisingly, gamma1 to gamma3 computable. So, computable partial functions between representations form a category, for those who know what a category is. So in the notes, there's a proof of this. I'm not going to do it. I mean, it's got. So, I mean, the idea is simple. You've got two computable partial functions, so they have computable realizers on words. You can, which are also partial functions. You compose the realizers on words, and that composition gives you a realizer on words for the composite function on sets. That's the idea. But because the definition of computable partial function is a little bit involved, actually writing out the details of that's a bit fiddly. So in the notes, just to illustrate that sort of line of reasoning, in the LaTeX notes, I've written out a proof of that in detail. Essentially, you just unfold the definitions, but there's a bit of work to do because there are so many details in the definitions. Anyway, it works, and we have nice properties of computable functions between representations. So another reason for not going through the proof now, I mean, it contains a lot of details. It's the sort of thing, I mean, it almost feels tropical in here. It's the sort of, I find, you know, in order to look at a proof with details in, I would need a big fan blowing cool air in my face or something like that. So instead of looking at the details, we're going to sort of bask in the heat and sort of look at just the overall impression of things. The LaTeX notes were done in the cool evening, written in the cool evening air last night, and so at that point it was possible to face them. So it's already 4 o'clock, but I do want to do one more thing before, because there's a natural breaking point. If I do a little bit, if I do a little bit more work, so I'm going to do that, and then we'll have a very short session for the third hour. So the thing I want to do is go back to the computability on the natural numbers. So we now have a notion of, we've got our general notion, so we could define computability for functions on the natural numbers in 3 ways. For each of our 3 representations of the natural numbers, or even in other ways, combining representations for the domain and codomain. I mean, you could think of many combinations there. All of them are equivalent. And how do we see that? Well, the key to that is actually saying that each of the 3 representations of the natural numbers is equivalent to each of the others. And that uses a very important notion, which is the notion of equivalence of representations. And this is a notion that makes sense if you have 2 different representations of the same set. So given 2 representations gamma 1 using the alphabet sigma 1 of the set X, and gamma 2 using a potentially different alphabet sigma 2, but of the same set X. So it's important that these are representations of the same set X. Just like we had 3 representations of the natural numbers. We say that gamma 1 and gamma 2 are equivalent. If we want to write that in symbols, we could use our equivalent symbol that we already used in a different way earlier. So what does it mean to be equivalent? Well, equivalent means we can compute from we can computably convert one representation to the other and back again. We now have a very easy way of saying that. So computing a representation, we leave the element that we're representing unchanged if we're converting one representation to the other. So we simply ask if the identity function X maps to itself on X, we ask for it to be computable from representation gamma 1 to gamma 2. So it can be computed by converting representation gamma 1 to gamma 2. and in the other direction by converting representation gamma 2 to gamma 1. So is both gamma 1 arrows gamma 2 computable, and also gamma 2 arrows gamma 1 computable. And as an exercise, so that you think about what this definition means, because the identity function is a total function, you can use just the definition of computability for a total function. So exercise, show that our three representations of the natural numbers are equivalent. So let's end this part with following observation. That the notion of computability is unchanged if you replace representations with equivalent representations. So suppose gamma 1, the representation gamma 1 is equivalent to the representation gamma 2. These are representations of x, or let's say of x1. And suppose also that gamma 2 is equivalent to gamma 2 prime. These are representations of x2. Then a partial function f from x1 to x2, so the partial function on the underlying sets is gamma 1 arrows gamma 2 computable, if and only if, I double f, if and only if it is gamma 1 prime arrows gamma 2 prime. And I'm going to actually prove this because if you just thought about this from the start, it feels a bit complicated to think about. There's actually a very simple proof now, combining the ingredients we've got, which is suppose f is gamma 1 arrows gamma 2 computable. I'll be doing the left to right implication. So then, by equivalence, we have that the identity on x1 is gamma 1 prime arrows gamma 1 computable. The identity function on x1, and the identity function on x2 is gamma 2 arrows gamma 2 prime computable. Of course, the definition of equivalence gives us the computability in the other directions, but these are the two we're going to need. And since composition preserves computability, so the composite, we can compose the identity function on x2 with f with the identity function on x1, composed with f, composed with the identity function on x1. Of course, that's just f. But the reason for composing them like this is we're composing this as a gamma 2 arrows. So there's a, well, this is a gamma 1 prime arrows gamma 1 computable. This is gamma 1 arrows gamma 2 computable. This is gamma 2 arrows gamma 2 prime computable. So this is gamma 1 prime arrow. We've just composed all the computabilities. We get that this is gamma 1 prime arrows gamma 2 prime computable. i.e. f is computable in that sense. And the other direction is similar. I mean, basically it's the same argument. So a nice abstract proof using the results that we've had before. Okay, so that was a very, very abstract hour. I think we need a good break after, so it's 8 minutes past, so we'll go until we'll resume at 23 minutes past, and the next hour, having done our abstract work in this sweltering heat, the next hour is going to be a little bit more concrete than what we've done so far. So anyway, let's have a break. Okay, so I want to hopefully not be too long in this part. The aim is, I first want to give an important construction on representations that will be very useful. And this is the construction of what are called product representations. Okay, can we calm down, please? So a product representation is a way of representing a product of sets. And a product, of course, of representative sets. So given representations of some sets, we form another representation of the product of those sets. So I was wondering whether to do just binary product or general finite product for some k. I decided to do the general case. So the general case is we're going to have k different sets, x1 through to xk, each with a representation. So suppose we have representations for gamma 1 is a representation of x1 all the way through to gamma k, which is a representation of xk. So we've got k different sets, potentially different sets. Each one is represented by its own representing function for its own representing alphabet. We define a product representation of the product set x1 times x2 times xk. So the set of all k tuples from the corresponding sets, x1 up to xk. The product representation, I'm going to call it gamma of gamma 1 times gamma k. Or maybe, yeah, well, let's leave that for now. It might be better to just use x1 to xk there, but anyway, there's a representation using a specific alphabet, which is I'll call sigma gamma 1 times gamma k. This is a representation of the product set of all k tuples, where the ith component of the k tuple comes from the set x sub I. Okay, so the product set x1 times. So let's write that. What did I do with the board here? Oh my goodness. So for some reason, classrooms here always have two board erasers. And this one in past weeks has had two board erasers, but I couldn't find the other board eraser today. So sometimes one needs to walk a very long way to get the board eraser. There we go. So anyway, these are product symbols, and this is the set of k tuples. And I simply need to define this, and it's not a difficult thing to do. I mean, how would you represent a k tuple? Well, we can simply represent it as a sequence of words. So a name for a k tuple, where the first element, little x1, comes from the set x1, and the kth element, little xk, comes from the set xk. A name for such a thing should simply be a sequence of names for the x1, the little x1, little x2, to the little xk, respectively. To be able to separate them, it'd be good to have some separating symbols so we can tell where one component starts and another one ends. So we're simply going to define our alphabet, sigma of, so the alphabet for the product representation is going to be, we're going to include all the symbols in the alphabets we've got representing the individual sets x1 to xk, and we're going to extend that by adding a new symbol, comma, which is going to be the separation. Now, really what I'm doing here is I'm making sure I'm adding a new symbol. So if the symbol comma appears in one of these sets, you need to make sure you add something else, like semicolon or something like this. But, or really you can consider this, if you like, as a co-product of sets. But I'm just going to emphasize that this must be different by writing a plus in here, meaning this is a disjoint union. So the comma is some new symbol. Yes?
Why is there not a star on the thing?
Good question. Because here I'm defining the alphabet. So the alphabet that we're going to use for the product representation. Oh, sorry, there should be a star on this sigma. Yeah, this one should have a star. But these ones shouldn't, because here I'm defining the alphabet for the product representation as the union of the alphabets as a finite set, the union of the given finite sets together with the element. Right, so that's the alphabet. The domain of the representation is the set of all words over this alphabet of the form where it should be a k-tuple of names where each of the elements is a name for an element of the corresponding set x1 through to xk. So it's those words over this alphabet of the form W1, comma, W2, comma, dot, 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 comma, WK. Actually, let's let me omit the W2, I mean, hopefully you can fill it in anyway. So it's of that form where each WI is a member, is a name for an element of the set X sub I. So in other words, each WI is in the domain of representation of the set X WI. And the action of the function gamma 1 through to gamma k. So we need to say how it's defined on any element of its domain. So this is a word over this product alphabet. So words of this form are always, words in the domain are always of this form, W1 through to k, separated by commas. And we simply define this to be the k-tuple of gamma, the element of the set, capital X1, named by W1. So we get that by applying the gamma 1 representation to, W1. Same thing for W2 and so on, all the way up to the name for the element of set xk named by wk. And it's as simple as that. Of course, if we wanted to, we could have put some open and closed brackets here and actually made the word look like a tuple with open and closed brackets, but there's no need to do that. We do need some separating symbol so that we can tell where the word for one element ends and the word for the next element starts. So very, very simple idea, and we can, using that, we get a product representation whenever we've got a represented set. And what's the use of product representations? Well, one of the uses is to answer the other question I had on the board at the beginning of the lecture. How do we define computability for multi-argument functions? Not happy with any of these black pens. A partial function f, a k-argument partial function, that's a partial function from product space to another product set to another set X, is defined the computable. Well, we'll use the, I'll simply use the notation gamma 1 to gamma k arrows gamma computable. Gamma is a representation using some other potential alphabet of the set X. This is also not a good black pen. Last one. So it's defined to be compute. So we define a multi-argument partial function to be computable if it, this is a good one. If it is, well, we simply use the product representation and our notion of computability for unary functions. So there we are, we're given this simple idea of having a representation of the product set, gives us an automatic definition of the notion of computability, but we don't need to do any work, basically. We automatically inherit from that a definition of computability for a multi-argument function. And there's a special case for this, sorry, special case of this. Having gone through a rather roundabout route, we're going to get to a definition of something that's of fundamental interest in computability theory, because it's a very mathematically very important notion of function. So as I said at the beginning, functions on natural numbers are very important mathematically and in practice, but not just unary functions, but also functions of multi-arguments on natural numbers. So a function, a k-argument function, a partial function, let's just say function with a symbol will make clear that it's partial, a function f, k-argument function on the natural numbers. So it takes a k-tuple of natural numbers as its argument. If it's defined, returns back a natural number, is defined to be computable if it is, well, we simply take our standard representation of the natural numbers and ask for it to be computable in the sense I've just defined. Sense I've just defined for any representations. So where of course here there are k representations involved in the domain, but they're all the same representation of the natural numbers. So here I'm choosing as the standard representation the one I used very first at the beginning, although turned in the other direction, so it goes from strings to numbers, which is the representation without needing zeros. And finally, so having done all this work, a very roundabout route to get there, but we finally obtained this definition. So it might seem like a lot of abstract stuff to do this, and indeed it is. So maybe an exercise would be to define this from first principles. I mean, you can easily do that, modifying the definitions that I had at the beginning. Although you do need some way of tupling the natural numbers. You do need some way of giving the inputs. Another way of doing that would be to give the inputs on a k-tape Turing machine. And again, you get an equivalent notion. In any case, we've got to this definition, and in doing so, we've developed some machinery which is going to be indispensable throughout the course, this machinery of representations. Right, so I just want to look at one other topic with representations, and that's we've considered the notion of computable function between represented sets. At the start of the course, when we were looking at functions on words, well, when we looked at Turing machines, we used the Turing machines to do two things. One was to compute functions on words, and the other, which was primarily our focus before this lecture, was to look at Turing machines as language recognizers. So as machines that would accept and potentially reject words.
Sorry?
Yes?
What do you mean with the gamma 1 times?
Right, okay. Oh, well, firstly, there's a mistake there. So thank you. And oh, bother. So this was supposed to be K. And the point is, I'm defining a notion of computability for a function in many arguments, using the notion of computability for a single argument function between two represented sets. And here the represented set of the code of the domain is the product set, and this is the representation of the product set, namely defined as on the top of the board. And the codomain is the set X, and this is the representation set X. So this is an instance of the notion of computability for a one argument function between two representations, as defined earlier. Anyway, good question, and there was the mistake that this should have been K. Right, let's maybe go back to the other board. So what I want to show is that represented sets also have, we looked at what it means to be a computable function or partial function between them. I want to show that they also carry a natural notion of decidable and semi-decidable set. So, given a representation, we've got any represented set, such as the natural numbers. The representation is going to be a partial surjective function onto the set X. A subset Z of X is decidable relative to the representation. So normally I would just write decidable, but to be totally precise here, I'm going to say gamma decidable, so decidable relative to the representation. If there exists a Turing machine M such that all words W in the domain gamma 1, so for all names, sorry, gamma, for all names of elements of X, two properties hold. If W is a name for an element of Z, then M accepts W, and if W is a name, so W is a name for some element of X because it's in the domain of the representation, but if it's a name for an element not in Z, then M rejects W. When we say that M decides Z. The thing to note here is that the Turing machine M, so I have touched this panel here, which is now falling off the wall. There we go, put it back. So notice that M decides Z, a machine M that decides Z is guaranteed to halt on all names on all words that are names for elements of X. But there are no guarantees about what it does on words that are outside, which are not names for X. So unlike when we were looking at decidability earlier, decidable languages, the Turing machine needed to halt on every word. In this case, the Turing machine does not need to halt on every word. It only needs, but it does need to halt on every word that is a name for an element of X. Okay, so that's a little subtlety here. And we say that a subset Z, subset of X is gamma semi-decidable. Again, if there exists and such that for all W, for all words W that are names of elements of X. So in this case, we require simply that M accepts W if and only if W is a name for an element of the set. So W is a name for something in X, but if it's the machine needs to just accept those words that are names for elements of Z, and it mustn't accept the others. But just like with the earlier definition of semi-decidability, there's no, if you're given a name for a word in X that's outside of Z, there's no requirement that the Turing machine M will hold. The only requirement is that the Turing machine will not end in the accept state on words for names, sorry, on names for elements that are outside of the set Z. So again, we say that M semi-decides Z. Sorry, yeah. So I hope you agree these are natural generalizations of the notion of deciding and semi-deciding a language, and decidable and semi-decidable language. So the one last thing to say about this is the following characterization, and
so once again, so this one, the gamma one has the representation, the product representation.
This is the product representation.
Yeah.
And gamma is the representation of the code.
Yeah, because we wrote it big gamma and then index the product thing.
Ah, right. I did. Thank you. I should check my latex notes to see how big this is.
In the notes, it's just the product.
Right. Yes. So this is an ill-chosen notation. So when I first defined it, I was actually unhappy when I wrote it on the board, and I was going to change it to something else, and I should have referred to my LaTeX notes to see. But anyway, just so that the board is consistent with itself. Yes, so thank you very much for the points there. So, but indeed, this is the point is this needs to be the product representation, and it would have been better to call it that, in which case I should have called it that up here, and that's, you say that's what I did in the LaTeX notes. So in the cool air of yesterday evening, my thoughts were straight, and I did something sensible, and here I was going on autopilot, so rather than referring to my notes. Right, anyway, what I want to end with is a nice characterization of decidable and semi-decidable sets. So I'm going to define a set B, bold set. This is the set of bits. So it's just the two-element set 0, 1. I'm going to give this a standard representation. I mean, that's a kind of stupid thing to do because bits are words themselves, but just so everything fits in the same framework, we're going to give this a standard representation. So gamma B is partial function from the Boolean words over the Boolean alphabet to the set of bits B. So I'm going to represent each bit by itself, the single element string that has that bit. So, so the domain of the Boolean representation is just a set of strings over the Boolean alphabet, which is, of course, the set B itself, consisting of those strings that have length 1, so either 0 or 1, and gamma B applied to 0, 0, and look, the gamma B is just the identity function. Gamma B applied to W is the word is either 0 or 1. So we've got a standard representation of the two-element set of bits. That's putting something very simple into the slightly complicated framework of representations, but just so everything fits in the same mold. Now, for a subset Z of a set X, we define two functions associated with it. Its characteristic function, so that's often written as chi of Z, also called indicator function sometimes. So this goes from the set X to set of bits or booleans, 0, 1. And I'm going to define another version of the characteristic function, a partial characteristic function. And that's, I call that chi superscript P of Z, the partial characteristic function of Z. That's another function from X into the set of Boolean bits. It's now a partial function. And these are defined by the characteristic function or the indicator function you will have all seen before, in one guise or another. So the characteristic function of Z is defined by maps an element of set X to 1 if X belongs to the subset Z, and 0 if X does not belong to the subset Z. So simply saying, give me the truth value of X belonging to Z. 1 if it's true, if that statement's true, 0 if that statement's false. Partial characteristic function is defined to be, again, 1 if X belongs to Z, And undefined, it's a partial function, so it's undefined if x does not belong to set. So similar, but instead of using 0 to say we don't belong to x, we give an undefined value. Something wrong with how I've written this? Does anyone know? So I should, instead of equals, I should use the clean equals I introduced earlier, because when I use equals, I mean both sides are defined and they're equal, which is normally, you only use equals between defined things. But here I want to say this partial function is defined if and only if the right-hand side here is defined, in which case it's equal to the right-hand side. The right-hand side can, of course, be undefined. So up arrow here means undefined. Maybe we already did that earlier. What I want to end with is the following proposition, which maybe I call the theorem in the notes, I don't remember, it doesn't matter. So the first one is that a subset Z of X is decidable is gamma decidable if and only if its characteristic function is computable, which means gamma to, so gamma is the representation of X, so it's computable with respect to the representation of X to the obvious representation of bits. And we have the same for semidecidable. Semidecidable if and only if the partial characteristic function is computable. Here at the top line, I've given the precise version where I'm referring to the representations. But always when we're talking, as I've already said, we kind of know which representations we have for the sets in question. So, so here the representation for the set X is gamma, and for the set of bits is gamma B. So normally what we just write this in the following shorter way, that a subset is decidable if and only if its characteristic function is computable. And it's semi-decidable if and only if its partial characteristic function is computable. Now in the notes, there's the start of the proof of, there's the proof, most of the proof of the first statement. I mean, it's basically more or less an unwinding the definitions. The idea is simply this. Decidability, you have a Turing machine of the language acceptance type that either accepts or rejects in this case. We turn that into a functional Turing machine that runs the first Turing machine. If it gets to accept, then erases the tape and writes a 1 on it. If it gives reject, then you erase the tape and write a 0 on it. From that, you take a Turing machine of the language acceptance type and you transform it to one that's a Turing machine of the function computation type. And in the other direction, just do the opposite. You run the function computation Turing machine. You then look at the output tape and see if there's a 1 or a 0 on it. One of the two must hold if you're representing the characteristic function. And depending on which of those two is on the tape, you then go into the accept state or the reject state. And something similar works for semi-decidable, we only deal with the accept state. So that's the outline of why that works. This is a fundamental equivalence that decidability corresponds to being able to test and give a Boolean result, a truth value as a result. True if you belong to the subset, false if you don't belong to the subset. Semi-decidability corresponds to being able to test and give true if you do belong to the set, and no guarantee, well, partiality, you just go into a loop if you don't belong to the set. Right, so in case any of you are missing the clock on the back wall, here it is. So basically, it's time for the end of the lecture. So, goodness me, let's hope the temperature, you know, we're heading into the autumn now. Maybe the temperature will come down a little bit by next week. Let's hope so. So I should be in touch with some of you. Actually, let me stop the recording. I'll be in touch with some